Okay, Doc. So we are going to get started on the lightning talks. So we have 9 talks lined up together. We've been given instruction to the presenter to prepare a talk of about 5 minutes. So 5 minutes is really not a long time to say much. So basically, it's really a sneak peek of their research, of their data, and the goal is to get started get starting on conversation, and we can go over lunch break for conversation. The way we're going to do it is we're going to do the 9 talks in a row, one by one, probably 5 minutes per talks, 1 minute to not stress too much, but to change speakers. All speakers are here, 9 of them, and we will open up for questions to any of the speakers at the end for 10 minutes. That makes sense? So just to give a background on the speaker, we have 9 talks. 3 persons are from Anschutz, and then 6 persons are from the Denver campus. We have people from mathematics and statistics, computer science, geography, and communication. Okay, so a little bit of everything. That was the goal, trying to celebrate all the achievements and trying to learn from each other. So I'm going to get started with Hamilton, and here we go. So the first speaker is Hamilton Bean from the Department of Communication.
Thank you very much. So the title of this project is Thwarting Russian Online Disinformation, a Rhetorical Analysis Artificial Intelligence Pilot Study. I want to emphasize this is the very earliest stage of this project. I want to acknowledge the other members of our team, Farnoosh, who we met earlier, Hadi Jafarian, who we'll hear from later today, and then Stephen Hartnett, who is also in the Department of Communication but cannot be here today. So as we know, the Russian government interfered in the 2016 presidential election. One of the ways that they did that is by purchasing social media advertisements and making social media posts. So I'd like to play a little game with you. Can you spot Russian messages? So what I'm going to do is show you 6 messages. You raise your hand if you think it is of Russian origin. If it's not Russian, leave your hand down. Everybody understand? Okay, here's the first message. Raise your hand if you think this is Russian. Okay, this one is not. Raise your hand if you think this is Russian. This one is. How about this one? Raise your hand if you think it's Russian. It is. How about this one? This is not Russian. This one? This is a Russian ad. And finally, this one. Not Russian. So stakeholders do not know which types of rhetorical appeals predominate in Russian disinformation. We know that it is all designed to weaken the centrist core of American politics and to foster division, social division. But we do not know the specific kinds of rhetorical appeals that occur within that universe. Also, we do not know much about how social media gatekeepers attempt to distinguish Russian disinformation from homegrown US rightist or leftist messages that have similar themes and ideas. Therefore, in this study, we scrutinized thousands of known instances of Russian online disinformation drawn from the US House intelligence community. Thank you, Larry, for the idea of other people's data. This is where our data comes from. In an attempt to categorize types of rhetorical appeals along a continuum of political action, exploring whether and how such an approach may be amenable to machine learning and artificial intelligence techniques. So here is the rhetorical continuum. You can ignore the x-axis for a minute and just look at the y-axis. So the blue represents the centrist core of American politics. As you move up the axis towards calls to violence, we go through the levels of stoking anger, calls for change, and then calls for violence. If we move down the axis towards trending toward nihilism, we go through the stages of cynicism, distrust in the system, and apathetic paralysis. This model was developed by Stephen Hartnett in the Department of Communication. So based on this model, we have 2 research questions and then 2 sub-questions. The first research question is, can we distinguish types of rhetorical appeals from encouraging social division to advocating armed aggression? Can these be systematically identified in Russian online disinformation? And then the second question is, if that's possible, if analysts can do that, can we teach machines to do the same function? The next question is, can Russian online disinformation be meaningfully distinguished from US leftist or rightist messages promoting similar ideas? And as we saw just a second ago, this looks a little bit harder to do, but we're still going to try. And if that is possible, can we teach machines to do the same thing? So it's a 2-phase project. The first phase requires us to label the Facebook and social media data collected by the US House of Representatives, and then we will consider 2 data modalities. One is content-based modalities, so textual data, visual data, and then social context-based modalities, including user data and network data. We plan to develop an ensemble model for disinformation detection, considering these 2 data modalities, and developing an LDA model for the labeled Facebook ad body, and enhance the model by incorporating the prior knowledge that we're going to develop in the rhetorical analysis. Thank you.
Thank you. Thank you. Thank you, Hamilton. So I remind you, it's hard on the audience. Everybody has 20 questions for Hamilton, and you have to remember the name of Hamilton, remember the question for the end, okay? So that's how, okay? We are not going to ask questions. I have plenty of questions myself. So our next speaker is Kathy Colborn from CU Anschutz. She's an assistant professor in the Department of Biostatistics and Informatics. Thank you.
Thank you. Yes, so I added Department of Surgery because on Tuesday that will be my new department. So this is a project I've been working on for a couple of years with the Department of Surgery. Give you a little background on the data. So the American College of Surgeons National Surgical Quality Improvement Program began in 2005 with the goal of assisting hospitals with identifying and preventing surgical complications. So each participating hospital trains nurses to do manual chart review to identify up to 30 days postoperatively who experience one of 18 different types of complications from surgery. And so at most large volume hospitals like the University of Colorado Hospital, about 10 to 15% of patients' charts are evaluated because it's a very time-consuming and expensive process. Hospitals have to pay to participate in the ACS-NSQIP program. And then the national data are available to anyone within the ACS-NSQIP, and there's over 700 hospitals that participate currently. So it's considered the gold standard for identification of postoperative complications. But, of course, manual chart review is expensive and time costly, so we wanted to develop a way of doing this in an automated way using the electronic health record. So at the University of Colorado Hospital, there's about 13.5% of patients in the ACS-NSQIP over the last 5 or 6 years that experienced a complication. So we've done this already using typical regularization techniques like the lasso or elastic net models. But we wanted to explore the use of a somewhat new technique called the knockoff filter, which was introduced by Barbara and Candace in 2015 and then adapted in 2018 for non-Gaussian outcomes. And the goal is just to identify a generalizable model. So in the data set we're using, there's 6,840 patients. We've done supervised learning, so we use the ACS-NSQIP outcomes data and we match that to patients' electronic health record. data for their covariates to see if we can essentially mimic what the nurses are doing in an automated way. So if we take sort of an EHR dump for these patients, we have ICD-9 codes, medications, CPT codes, their ASA class, we end up with about 2,555 variables. And to kind of fast forward a little bit, because the knockoff filter is probably new to a lot of people, basically the idea is we want to control type 1 error. So when you fit a regularization technique, you often make false discoveries. They're very useful for P much greater than N problems. However, you still end up with a lot of false discoveries. So the goal of the knockoff filter in a nutshell is to identify that subset of covariates that are important for predicting the outcome. But we want to set lambda, which is typically our penalization parameter, so that we are controlling the false discovery rate. So if we define this in the typical way, it looks like this. But in summary, the knockoff variables that we create are constructed so that the correlation between the distinct knockoffs, so let's call those X tilde J and X tilde K, is the same as those in the observed data. The correlation between X sub J and X tilde K for J not equal to K is the same as the correlation between the original variables. And then the knockoffs are created without looking at Y. So you generate a whole knockoff data set. This is not a fast procedure, I'll warn you. I was up very late last night trying to produce these results. And so if we compare this, let's say we have a training and test set, which I didn't point out, but it was in the slide. Older data is our training set, newer data is our test set. We can compare two models, one produced using ElasticNet for model selection, and then one using the knockoff filter. I chose two different thresholds for classification here just to try and get the comparisons a little bit more similar between the ElasticNet and the knockoff filter. But you can see you get very similar performance, and you're using a fraction of the number of variables. So the knockoff filter model used 36 variables, and ElasticNet selected 163. So the goal was parsimony, and it seems as if we don't have much loss of predictive performance. So I have 0 minutes left, so thank you.
So thanks a lot to Kathy. We're going to go to the next speaker. The next speaker is Jan Mandel. So Jan is from the Department of Mathematical and Statistical Sciences. He's full professor. And I'm going to let Jan speak.
Thank you. How do I control that? Let's see. Okay, so first, postdoc Angelo Farguel is here. He actually produced much of the machine learning code and the movie at the end. Okay. All right. So when I read the abstract, turns out there is just no way how I can say even half of what's in there. So I decided to throw up one complicated picture, which is the system as a whole. And each of the boxes is a software system which took many people years to produce. So that's a result of many years of work by many people. And the movie shows one visualization of fire and the fuel moisture field. The fuel moisture field is on the bottom, and you can see that when it gets yellower, which means the fuel is drier, the fire actually gets stronger and makes more smoke. And it's, of course, time-lapse and very fast. Every of those periods takes a day. You're, in fact, fairly amazed to see how the weather waves are producing corresponding changes in fuel moisture. So this is actually one thing that allowed us to model fires, how they change overnight. You know that at night, fire actually is slower, and here's why the fuel moisture goes up. This being data science meeting, I picked just one part of the project having to deal with data, satellite data, namely, because we would, like in the old times, we would give the computer a point to start, which is nice in theory, but we don't really know the ignition point, and in reality, the ignition isn't known until the report is produced, and by that time, the fire is basically over. So, what modeling? But satellites are always there, and this NASA visualization shows a satellite that's polar orbiting. The Earth is turning under it, as you can see, and the satellite is scanning the Earth, flying over the same place on the Earth twice a day, monitoring fires, among other things. But the challenge is, how do you actually start the model from such satellite data? How does the data look like? So what you are going to see is a unique visualization of satellite data. So every flash is one satellite overflight. The green pixels are pixels where the satellite has seen no fire, so we call it detection of clear ground. The red pixels is fire. And now how do you make some sense out of it and actually recover the fire parameters from that? One thing that's unique to this approach is we actually take the green pixels to be data because they are important to us. Also notice that the pixels change in size as on different flashes, and this is because the satellite is looking at different angles, so the pixels get bigger. Sometimes the backside of the mountain is invisible when the satellite is really looking sideways. So how do you make that into some orderly kind of fire progression? Well, the key is convert it to a separation problem, and this is where machine learning comes in. We represent the fire in three-dimensional space, so we have two-dimensional surface and then time is vertical. And if you visualize the satellite data in this three-dimensional space, then the red pixels are inside, this is where the fire is, and the green pixels are outside, so this is where the fire is not. So to find actually the extent of the fire is a separation problem. You separate the burning pixels and the not burning pixels in time space. And here is how it works. You can see on the left is the separation surface and the data. On the right is a movie, so first you have just flashes of the fire. So this is what a satellite data actually looks like. You get flashes and what kind of sense to make out of that. So let's see, in a second you will see the perimeter of the recovery potential.
Do you have a better movie without
yeah. For sure.
So now you can see that the support vector machine, the interpolation, separation, actually recovers the fire perimeters, and they are nicely stretched on the pixels, and we use that to start the model, because the model starts, we use it to start the model when we already get the data. Thank you.
So this was Jan Mandel. Thanks, Jan. The next speaker is Michael Rosenberg. He's assistant professor at CU Anschutz Medical Campus, medicine, cardiology, and cardiac electrophysiologist, School of Medicine. And Michael is going to speak to us about going long, making the transition towards quantitative individualized medicine. Thanks, Michael.
Thanks. This was an hour-long talk, so this will be interesting to see what happens when it goes to 5 minutes. These disclosures. So if you want evidence that we've entered the era of quantitative medicine, you don't need to look any further than statins. This is what many people think is the most important medication discovered in the last 50 years. It's reduced millions of heart attacks and coronary disease worldwide. It's the largest selling class of medications. The reality is nobody ever feels better starting these. The only reason we know that these work as effectively as they do is because of numbers, because of statistics. The problem is that when it comes to treating patients, we treat the person sitting in front of you in a clinic and not big populations, which is fine, you know, if you're in the lake where the average depth is 3 feet, but if you're this guy and that's found the little channel, you're not doing so well. And unfortunately, in clinical medicine, we have zero tolerance for these events. So the way we get around this, or one of the ways we proposed, is to basically go long, which is to take a single person and collect lots of data on them over a period of time. And to just kind of give you an example of how we envision this working, we'll take a clinical vignette. This is a typical patient, 47-year-old with migraine headaches, occur roughly once a month. They're associated with an aura, pretty standard for migraines, right? Making the diagnosis. Well, how would we treat this patient clinically, currently? Well, we would use evidence-based medicine, for which all of these things listed are associated risk factors. But we would just tell her, well, why don't you try to avoid caffeine, or maybe avoid alcohol, or get more sleep, or avoid stress, or exercise more, or maybe if you're exercising too much, exercise less, or to take this medication or stop taking that medication, and come back and see me in 3 months, and we'll see how it's going. And if you were able to find parking and didn't have a headache that week, then you'll be happy, and if not, maybe less happy. And the reality, that's the standard of care for the most part for medicine these days. Our approach is sort of a little different. It's basically, we say keep a log of headaches each day. Yes, no, perhaps wear a sensor, have some kind of independent orthogonal data to collect on your activities or whatever could be risk factors, and come back in 6 months. Is there a time somewhere, or am I just kind of going? Okay, great. So basically, this is how it works. You get your data 6 months later, and you're able to look at correlations. You're able to look at cyclical patterns. You're able to do statistics on this to find risk factors that might be associated. So how this would work in the clinic is basically the patient comes in. We have the data now in front of them, or in front of the provider, who says that it looks like sleep the night before has an inverse association with your risk of having a headache the next day. We also noted, because we did some time series analysis, that your sleep has a 21-day cyclical trend. The patient kind of, thinks about it, says, well, every 3 weeks I'm responsible for helping my daughter's yearbook committee. I usually wake up early those weeks. Well, the provider says, why don't you try going to bed earlier the weeks that you're doing the yearbook committee? Collect some data, come back in 3 months, see how you're doing. Of course, the beauty of this is we're collecting data. So we know, one, that she's changing her behavioral patterns, and two, we can see that she's having less headaches, and more importantly, you have your happy patient. So basically, how does this work? The reality is you can do this with any outcome, as long as it's, repetitive and it's something that can be measured. You collect it, you measure it over time. The important thing, you model it statistically as well as you can, and there's a number of different ways to do this. We don't do them a lot in clinical research, but they're mostly time series methods. Whether it's, long-term average trends, you can do all kinds of different functions. You then collect as much data as you can about other risk factors, and you find ones that are correlated. The beauty of this is that because you've been able to model your outcome, you can forecast what would you be expected to do so that when you do an intervention, you can see the difference over time. So how do we collect the data? Right now, we're developing an app. We have a pilot study going on. If anyone's interested, let me know. We're looking for volunteers. It allows you to track the data. It does correlations for you. There's also a website called udatalize.com where we've been playing around with Fitbit analysis. If you have Fitbit data, you can go in there and link to your data, and it'll run an analysis and let you compare with friends and things like that. This is our group. We're the individualized, not to be confused, I guess, with IDEO today, the Individualized Data Analysis Organization. The important thing of this is that you need clinicians and analysts working together to understand the statistics and how they can be applied to populations. And that's it. Thanks.
Okie doke. Thank you. Thanks, Michael. Thanks a lot. And the next speaker, and he's already ready to go. That's wonderful. So this is Ashish. Ashish is so we're going to change campus. Michael was from the campus on Anschutz, and we're going to go to the Denver campus. We're going to change department. This is computer science department, but we're going to stay on the theme of medical, and we're going to hear about brain tumor and MRI images. Please.
Thank you. I'm Ashish. I need to go back to Dr. Hunter's comment that, yeah, I'm a computer scientist, but I do somebody else's data analysis. And I do machine learning and deep learning. I run machine learning lab at Sherep in the downtown campus. So this project, with collaboration with Dr. Natalie in the Anschutz Medical Campus, and one of my master student, Julien, is currently has worked over the summer, but this is a developing story to classify cancer subtypes looking at MRI images that we have. And one of the big issue that we have is the brain tumor is second most common malignancy in childhood after leukemia. So that's an essential study that we found, and there are 4 subtypes that we were interested: medulloblastoma, DIPG, ependymoma. I'm not domain expert. Maybe I need to take that class, but and edema. So there are 4 different subtypes and classifying. So we need to build from data of a bunch of MRI images very similar to this to classify what type of tumor that patient is suffering from. And gladly, we were looking at the publicly available data first, and then we have the collaborators' data. But there's 4 different types of a sample that we can collect, and this is just one of them. So there's T1, T1C, T2 weighted, and the flare of the same patient. And this is since this is a MRI data, it's not a single image, so it's a slide of image. It's a multi-dimensional, 3-dimensional essentially. And this is actually what you're looking at is slide 100 of that particular sample number. Since this is anonymized, this is definitely identified by an ID only to us. And the data also contains labels which a clinician manually highlighted at slide 100, there is a tumor present. So if you take a look at that, there's not many data that we have. For HGG, there's 262, and LGG 100, close to 200. So there's not many data that we have in the repository to build a classifier of it, out of it. And also one other issue that we face is rather than feeding all the data into building a classifier, might be less meaningful to characterize what type of class that we're looking for a brain tumor. So what we are looking at is first we'll do segmenting the tumor, and we'll only feed the segmented volume of the brain tumor into building the classifier. So there's for segmentation, this is part of the segmentation challenge that we worked on over the summer. There is performance metrics that we worked with, but yeah, it's one of the it's not, since this is segmentation. So in measuring the performance of the segmentation, one actually metric that we typically use is intersection over union, the IOU and Hausdorff scores, and there's several other sensitivity and specificity, but these are the performance metrics that we use to evaluate and train the model that we like. One popular these days, actually, I'd like to attribute Dr. Ronberger's work back in 2015. Since this is a first, we need to segment the brain tumor. So in order to segment, what we need to do is either, since this is a semantic segmentation, we need to highlight, classify each pixel of a slide of an MRI, multimodal MRI data, whether it belongs to a brain tumor or not, or whether it's a part of a brain or background or a tumor pixel. So there is many different approaches developed, but in 2015, it's part of medical image competition also, they participated. So this is the architecture they came up with. It's a very intelligent and clever idea that compresses. So kind of a symmetric architecture of a deep neural network. It's a variant of convolution neural network, but it doesn't suffer much with less number of data that we are facing in this particular project, because we only have less than 500 sample in the repository. So we cannot afford training a convolution neural network to build a model. So this is one of the architecture that solves that problem. And on the left side, it has a U-shaped structure. From the left side, it compresses from the original MRI slide and down to the smaller version of the image, getting rid of irrelevant information other than the tumor, but preserving the location and the shape of the tumor. And then on the right-hand side, so once it has reached that point, then it upscales the image, considering only about the tumor that is present at that particular point, and going up to the scale where the initial MRI image that we need. So in that particular case, so in the output, we will only extract, we will only get the MRI, the image with the tumor only. So it's very similar to the one that you see here. So our goal is to get a close match. So this is the idea of UNet, but since this works on a 2D scale, the image that we have, MRI data is multidimensional. It has close to 155 slides in one of the T1 image or T2 image, and flare and T1 adjusted. So what we need is a three-dimensional modeling. We need to calculate, segment the volume of the tumor rather than identifying a two-dimensional boundary of a tumor. So this is the convolution that we used. This is deconvolution to upscale. So in our project, we consider all these different modalities all together, and we integrated them and then once we have the tumor, we collect all the features of the tumor to classify the subtypes of the brain tumor. And the classification performance that we have initially has promised is not based yet, so we're still working on that.
Thank you.
Thank you very much.
Thank you, Ashish. Thanks. Yes, thanks. Thank you. Yes, it's Amy. So the next, so thanks a lot to Ashish. The next speaker is Amy Roberts. She's from the College of Liberal Arts and Science. She's in the physics department, and she knows everything about dark matter.
What we know about dark matter is very, very little, and I can say that very conclusively. So I'm Amy. I'm an experimental nuclear physicist. I'm the person who makes sure that the data gets from the awesome detector to the hard drive, and that scientists can actually do science with it. So that's a fun, a lot of times we feel like that's a very hard real-time system right there. Okay, so one of the things, and what I'm going to focus on today is, in my group, we spend some significant amount of time making the analysis environment more accessible for people who are programming novices. So once you take your data, you want to do science with it. And I'm going to describe in an ideal world sort of what that scientific process sort of looks like. So you have your data. Your data is, maybe it's in some kind of comma-separated value file. Maybe it's in JSON if you were scraping off the web. Maybe it's in HDF5. But often you have data that's in some standard format. And so you get your data, that's sort of step one, and then you pull your data into your favorite analysis environment. So in this case, you've got a comma separated value file. You can pull that into Excel if you want to. And honestly, in experimental nuclear physics, a lot of times Excel is the appropriate tool, but that's great. You can pull it into Excel, you've got it, you can do your analysis. Okay, so there was a comment earlier that physics has done a really great job with openness in their data, and that's absolutely true in some subfields of physics. So the high energy physics field is a field that has really worked hard to develop their software infrastructure, and that software infrastructure is a significant part of what makes that openness possible. Let me explain what this data analysis is going to look like in an experimental nuclear lab. So, in an experimental nuclear lab, you are going to use a data acquisition system that was written 10 to 20 years ago. And that data acquisition system is going to write that data in a very concise format. It's going to write it in a custom binary format. So here's an example custom binary format. You'll have, the initial byte will tell you how long the next string of characters is going to be. So in this case, this first byte tells us that we're going to have 3 characters, and then you have your 3 characters, and then after that you have 1 byte that's reserved for the age of the animal and 2 bytes that are reserved in Little Indian for the weight of the animal. Okay, so that's like sort of a straw man example, but that's a fairly typical type of format that you might expect to see coming out and being stored on disk in an experimental nuclear lab. Okay, so what do you do to analyze this? So what you do is the first step is you get your data. Great. If you have your data in hand, then what you need to do is you need to find the code that someone else has used to analyze exactly that type of data before. Okay, good luck. You'll need it. That code, I can promise you, will be written either in Fortran or in C++, and it will be difficult to compile. It will need a specialized compiler in some way, Intel Fortran specialized for Fortran 77 on an AIX machine. You can compile it there. So once you have your code and you've managed to compile it, congratulations. That probably took you 2 to 3 months if you're a graduate student. Then what you do is you need to find an expert to help you modify this code. Because usually what you have is you're doing some experiment that's almost exactly the same as the person who used this code previously. But maybe you're doing something a little bit different. Maybe you've added a detector, and you need to make sure that you get that information about the detector in your data analysis. So what you need to do is you need to find an expert, and you need to get them to help you modify this code, and then you can do your analysis. What you can expect if you're an experimental nuclear physicist is that there will be 1, 2, in an ideal and amazing situation, 3 people in the world who know how to do that. They're all really busy. One of them is probably dead. I've seen more PhD thesis graduations delayed by this than I can count. Okay, so is there a solution? So what I would suggest is that we really need to find a way to bridge the custom binary data environment to the community-supported tools that we all can use, right? So if you can bridge that custom formatted data and pull this into a Python environment and use the pandas data package, then you have a much more accessible analysis environment. So there are actually several data description languages that are out there. What these languages do is they allow the scientist to describe the format of the data. So it's not prescriptive. You can have your data in whatever crazy format your data is in, but you describe that format, and then you have a set of tools that you can use to pull those into an analysis environment that's a little bit more manageable. Okay, so that's one of the things that my group is working on. So my group is working on taking one of those existing description languages and writing tooling that will pull that into one of the standard data environments that's used in high energy physics. So if you are also in this boat of being in a community that has masses of custom formatted data that's causing difficulty in your analysis environment, definitely come talk to me. And that's all right.
Thank you. Thanks a lot, Amy. So while the next speaker is getting set up, I just want people to realize that this is data science. So if we didn't know that Amy was from a physics department, we would thought she was computer science. And Ashish pretty much gave a medical talk and he's from the computer science department. So we should have hidden the department. I think it's really data science, and it's kind of wild and crazy, and I love it. So anyway, so the next talk is from Adi, and it's about adversarial machine learning. So please, Adi.
Hello, everyone. I'm Adi. My area of expertise is cybersecurity. In this talk, I'm going to go over adversarial machine learning and a brief overview of it, and also placing our research in the bigger picture of it. So what is adversarial machine learning? Adversarial machine learning is a novel class of attacks that are actually aiming to either deceive machine learning models to misclassify inputs or try to learn the training data of the model or the parameters of the model. So it has different types. So they have been around for 10 years, but they have gained more popularity and more, examples of them have been shown in recent years. They have different types. The two fundamental types are model evasion and model inversion. Also, there are other types like model extraction that we don't cover here. So what is model evasion? The goal of model evasion is to perturb an input so that to deceive an ML model to misclassify an input, for example, an image. So, for example, look at this example. On the left, you have a picture that the ML model has correctly identified as a panda, but then here, using the gradient of the model, the attacker tried to add a small but intelligent noise to this input, to this image, so that deceive the model to misclassify it as a given, right? So you can see what are the implications of this. For example, imagine a facial recognition-based authentication system, right? What the attacker would try to do here is just to evade the model, right? Make it, just misclassify an image as a person who is authenticated. But then another class is model inversion, and the goal here is different. The goal here is to recreate the training data. For example, the same example of facial recognition-based authentication. Here the question is, who are the people who are working for this company? Who are the people that this ML model would classify as authorized? And here we start with a black image, but then using the gradient of the model, we start to change it step by step, iteratively adding noise to it until the desired classification is achieved. So an example is here. The picture on the left has been used as a training sample for an ML model, and the picture on the right has been regenerated from a black image using the gradient of the model, and you can see that it is kind of like it has been quite successful. So what we are trying to do is to understand what we're trying to do. There are two types of setting in adversarial machine learning attacks: white box and black box. In the white box, as the name suggests, you know the parameters of the model, you know the gradient of the model, so you know generally the structure of the model. But then in a black box setting, and most of the work on model inversion have been focused on the white box approaches, but in a black box setting, you only can query a model. You do not have any other knowledge, especially the gradient of the model, which is necessary to launch the attack. So our goal is to come up with new gradient approximation techniques and to perform black box model inversion attack, and also develop defense mechanisms. Always that's the purpose in cybersecurity. Once you come up with an attack, is just to understand, how that attack is launched and come up with defenses. This research is being conducted in my lab, Acid Lab in the downtown Denver, with my PhD student Thomas Beckman, under co-advising of Dr. Bishwas and Dr. Banai Pashan. So the focal research challenge here is, that we have here is that, in a white box setting, since the gradient is available, model inversion is easy. But in a black box setting, we have to approximate the gradient. So we are looking at two types of approaches. The most important type that we're looking at is that can we create substitute models? So we are in a black box setting. We want to create substitute models that mimic the behavior of a target model, and then hopefully we can use the gradient of the substitute model in place of the target model as an approximation for the gradient. And also we want to look at numerical approximations and compare the two. So this research is in infancy. Hopefully we'll have a submission on it in a month or so. Thank you very much.
Thank you. Thanks a lot, Adi. So the next speaker is Fuyong. Fuyong is from the Anschutz campus. So I'm going to let Fuyong speak about KaiNet. Thanks, Fuyong.
Okay. Hi, everyone. Today I want to share one of our research projects, which is use deep learning to quantify the digital pathology images. And this project is a collaboration with the Department of Pathology in the Mandel campus. It's still ongoing, and today I will briefly introduce the background and the major idea. Okay, so this is the image shown on the right is the example image of the pancreatic neuroendocrine tumor. As we can see, there's a lot of different kinds of cells there. And the pathologist would like to determine whether this patient has disease or not based on this image. And if the patient has disease, and it's a low grade, intermediate grade, or high grade. So, but this grading depends on one kind of biomarker called Ki-77 labeling index, and which is defined as the number of immunopositive tumor cells over the number of total tumor cells. So, as shown in these two images. In these two images, we can see that we have different kinds of cells, immunopositive, positive tumor, immunonegative tumor, and non-tumor cells. And basically, the Ki-77 label index assessment is a cell detection classification problem because we want to quantify and classify all the cells in the images and differentiate all the cells in these two images. And the reason why we want to do this project, because nowadays in the hospital, most of the time, the pathologists do this manually. They use their eyeball to estimate the number of different types of cells. So you can image that for large size image data, such as the one showed in the previous slide, which has tens of thousands of cells. So I believe that it will be very challenging and difficult to count different types of cells manually. So it will take a lot of time, and also you can have a lot of errors as well. So here we would like to provide an automatic method based on deep learning to do the counting. So this is the architecture we provide, and actually it's based on the unit architecture. We modified the architecture, as Ashley just mentioned a few minutes ago. And this is the end-to-end model learning. And given the input image data, you will see we can directly the output here, the final output here. So given the input image data, the architecture will directly produce a prediction map. And in this prediction map, the local maximum will present the position of the cells. And here, because we have different types of cells, so in the final output, we need to provide different type of the prediction map, and each of them will correspond to one class of the cells. And another contribution for here is that we introduce another branch which is used to separate the tumor region from the non-tumor region here, because in real applications, when the pathologists do the cell counting, they look not only the cells themselves, but also the surrounding regions as well. So it's very common that the tumor cells are close to other tumor cells and non-tumor cells located in the non-tumor regions. So in order to encode this information to the model learning, we introduce a related task, which is to separate the tumor regions from non-tumor regions into the model learning. So we believe that this multitask learning can further boost the cell classification. And another point we want to emphasize here is that this architecture is entirely end-to-end and pixel-to-pixel. We don't need the intermediate steps, we don't need the feature engineering, and we don't need the cell segmentation, which is extremely challenging in real applications. So we do compare our method with some other deep methods. As shown in the left 3 column, and in the small black box here, it shows that some other state-of-the-art deep architecture can maybe fail in the cell detection and classification in this problem. And finally, and this is our team, and thanks.
Thank you. Thanks a lot. Thanks a lot, Fuyong. That was very interesting. The next speaker is the last, actually, so the last but not the least, it's Troy. Troy is from the Department of Mathematical and Statistical Sciences, and his talk is going to be about more education and teaching and Jupyter notebooks. So please, Troy.
I'm all that stands between them and lunch.
No, actually, we've got a question after.
Oh, yeah, there's that too. Okay, so yeah, Julien asked me to give this talk that has nothing to do with a research topic per se in any kind of specific sense, but more about how we maybe should be conducting our research in a way that enhances reproducibility and also allows us to educate students and train our researchers. So I also put up a lot of names here of faculty in the department, as well as Michael Pilosov, who's one of my PhD students, who's the architect behind a lot of the hub work we've done. So I know we have a plenary speaker after lunch who will be talking about Jupyter. You can read more about Jupyter by going to jupyter.org. That's Jupyter with a Y. That's the way it should be spelled. Jupyter is something that's kind of all-encompassing. It's very flexible in terms of what you can do. Over 40 languages already supported, including very popular ones like Python, R, and Julia. These are very common in data science and machine learning. And we're utilizing the heck out of it in the department. We have really integrated it into our numerical analysis, PDEs courses, numerical PDEs, Monte Carlo methods, a UQ class that's new, and Math Clinic, which gets to students thinking about how to even frame and properly ask questions before they're addressed. And actually, more recently in the summer, it was even taught in, it was used by Stephen Harkey in a number theory course, which is often considered a very pure, theoretical, abstract math course. And he was using it to expose students to how these concepts were used in like RSA encryption schemes. And a quote he sent to me was, I believe, teaching number theory without computations is like teaching astronomy without using a telescope. And so the Jupyter notebooks really allow you to fully integrate in a very easy way computations that bridge the gap between theory to practice. So it really helps turn students from thinkers into practitioners. So it's a really, really useful tool. I'm a big fan of it. What I'm showing here is just a movie of what I did in Calc 1, assuming students had no programming language, but just allowed them to give you a sense of notebooks if you haven't seen them before, that you can integrate narrative text along with multimedia, computational demos. This was the first lecture I gave in calculus when I taught it last fall. And it was just getting them a sense of, here is how you understand limits as, here's how you can conceptualize limits in terms of like going from average velocity to instantaneous velocity of an object. And so we could choose models of balls going up and down, model the position in time, and then play around with slopes of tangent lines or secant lines to understand what limits are. You can look at how to get hubs installed. So one of the nice things about a notebook is that it's like this living, breathing document that you can play with to understand these ideas. But one of the challenges that I'm sure anyone has encountered when they try to use computational software of any kind in any course or in their own research group is everybody has their own machine with their own operating system, and they're installing different versions of software, and what works on one person's machine isn't working on another person's machine. Hubs are the answer to that. All right, they're a unifying system. You create like a computational server where you load the hub. Everyone logs in. It removes all barriers for people to do this. In particular, you can think of this as addressing broadly equity concerns because there are students of means or grad students that don't have the money to have state-of-the-art laptops. Maybe they have a notebook, or maybe they just have a cell phone. Usually people just have those. You can just, with a web browser, interact with the hub and do all the coding from there. So they don't need a state-of-the-art machine. You're offloading all of that to some centralized machine that the department of the university can provide. And so you can then access the resources for these computations anywhere that you have network service, assuming that you can VPN wherever you've installed this hub. And then in research, it also helps enhance reproducibility because what's working on one person's machine is guaranteed to work on another person's machine because it's not their machine. They're just interacting with the hub. And this allows you to do rapid prototyping, easy debugging, and lead to shorter development cycles in your research. And you can use this for talks. Like what I'm showing here is I give my research presentations now in Jupyter notebooks and actually have a slide environment. So I'm presenting talks with really clean, beautiful looking slides. You can hide or show the code. You can focus on the concepts. I embed multimedia along with the narrative text in my talk. So movies, images. I'm showing simulations of cooking T-bone steaks because that's what I like to do. And what's nice about this as well is everything is very fully interactive with the computations you create. So I have examples within the talks, I think it's going to get to it here in a second, where I show figures and you can manipulate them because they are being generated by the code behind the surface. So you can resize images, you can zoom in, this is what's being shown here. And then at any time, you can just exit the slide environment, go back to the notebook, and show people the code, the details behind all the narrative. So this is what's, I think this is going to be at the forefront of how we're teaching, educating, and doing research, and broadly in math, but also in any kind of computational science and data science. That's all my time.
Thanks. Thanks a lot, Troy. So we are going to get prepared for the audience to ask some question. I'm trying to make eye contact with Daniel. Can you get some mic? So we had 9 speakers. So what we are trying to do now is put a slide with the name of everyone, so that if you ask a question, please say the name of the speaker first. We are going to do 9 questions is a lot, so we are not going to do it all. Okay, we are going to do a few just to warm up and engage with the audience. So who has a question? Who wants to ask a question to who? Yeah, let's go. So do not forget to say the name of the person, or maybe, that's it.
Hi, I can't read that first name, but the first gentleman who spoke about the Russian, thank you. Sorry. My question for you is, when do you expect your research to be completed on this? It's very interesting.
I don't think we have a completion date set. We're actually just beginning. We have an initial meeting to go through a first pass of the data on September 9th. Yeah, it's going to be a while.
Thank you, Hamilton. Is there another question from the audience for someone? Are you allowed?
I had a question for Katie Colborn. So I was curious about your model, because you mentioned that one of the motivations was that it's very expensive to monitor all of those charts for all of those patients. So are there pieces of sort of verifying the model that you're creating to flag for complications? I mean, do you have like a person go through the chart and then say, okay, yes, there was a complication, and then you compare that to your data to see that?
If I'm understanding your question correctly, we use a supervised approach. So the ACS NSQIP data are the manual chart review. And so we build a model not from the covariates that are measured in the ACS NSQIP, but through an electronic health record download. And so we hold out a test set. So we build a model in the training set, which is about 2/3 of the data, and then our test set, we evaluate, so those are observed, recorded, gold standard outcomes. And so that's what we're comparing against. If you scale this up and try to use the model in practice for all patients, you're going to have to just trust that your model is doing well, or ask somebody to do a random sample of the remaining people who aren't in the ACS NSQIP. And this is a problem, because the gold standard data set only covers about 10 to 15% of operations.
Thank you. Thanks, Amy, for the question. Thank Katie for the answer. One more question, yes, please.
This is also for Katie. How many variables were the nurses looking at? I mean, when they were analyzing it, as opposed to 2,555 with the machine.
Yeah, that's a good question. I wish I knew the answer to that entirely, but they do a chart review, and they also reach out to families and call them to confirm. So I think that the machine learning approach is always going to be at a disadvantage, because we can't follow up in that way. There's some people using the text notes. So the nurses have access to the text notes. So we just wrote an R01 actually to try and incorporate natural language processing on the text notes to try and extract additional information that isn't just coded data in the EHR. So we're hoping that'll help.
I think we got a question from Cyrus now.
So as an organizer, I'm going to just cheat here and ask one last question, if that's all right. So one of the things that Kevin talked about, and that is really interesting about all these tools, is they can be applied in a lot of different domains and disciplines. So this is open to any of the lightning talk speakers. As far as the tools that you're using, what are some distant domains or disciplines where those tools can also be used, or where you've seen them used, or where you could think of them being used?
You're right about that. So I guess I would say that this idea of describing the data format of the language really applies to any discipline where we have data. And I think one of the things that's really important to me is this idea of having accessible and reproducible science analyses. And so I think that, some of these common formats that we have are real, they're fantastic. But there's a lot of data that's not in that kind of standardized format. And so I would really say that I think this is a tool that at least in fields where, there really hasn't been success in standardizing a data format, there could be a lot of real value, because a lot of the analysis methods that we're discussing are difficult to do. And when you write a piece of software that's targeted only to one specific format, and then you can't use it on these other formats, you're really losing data in an unnecessary way. So I vote that we all record our data formats.